Welcome everyone to these intermediate experiments in electronics. Today we're going to explore transformers, specifically core saturation. We'll touch on concepts of safety. We'll explore how to measure the current waveform. We'll consider the magnetic field in a transformer's core and some of the limitations, including some cause and effect with the magnetic BH curves. And then we'll look at some of the next steps that you might like to perform. Here are the major parts for today's experiment. We have a junk box transformer that is set up for 24 volts AC. And we have a current transformer. I've selected the Charlie Sierra Tango TAC 1010 current transformer. It's designed to measure 10 amps, and it works very simply. All you need to do is pass a wire through the aperture of the transformer. And then on the output terminals 1 and 2, it will provide a voltage. So you can see that here. One turns through the aperture, and then there's a voltage developed on the output, assuming there's a 100 ohm burden resistor right here as RL. Based on this chart, it looks like there is a 10 amp current results in a 1 volt output as developed across that 100 ohm resistor. To increase the ability to measure small currents and to simplify the math, I have run a wire through the aperture of this transformer 10 times, which means that 1 amp of current will now appear as 10 amps as far as this transformer is concerned. So rather than having a 10 amp to 1 volt ratio, our device will now have a 1 amp to 1 volt ratio. For this experiment, we're going to use a variac, which is line powered. To that, we're going to connect one winding of our 24 volt transformer. For this experiment, we will not be interested in the output, which is to say we're going to use the transformer with no load. We're going to place that current sensing transformer on this line with its 100 ohm burden resistor. And remember that there are 10 turns through the aperture. We'll then use the oscilloscope to monitor the voltage here and the voltage here. We'll let this be channel 1, and we'll let this be channel 2. I almost forgot to mention, this transformer is hooked up in this direction. This is necessary because we are going to apply an excess voltage to the winding. As it's currently configured, we could potentially apply 120 volts to the 24 volt winding. As you'll see in a moment, that's not possible because it will destroy the transformer. However, we can apply lower voltages and we can incrementally increase the voltage to see what happens. In a moment, we'll get to that experiment. However, before we do, we need to review a little bit about magnetics. This is the BH curve, where this is the applied magnetic field, and this is the B field, which you could think of as the strength of the magnetic field in the core. Notice that there's a near linear relationship in this section, which is to say when you apply the magnetic field, there's a corresponding increase in strength. However, there's a point up here known as saturation. Right? So we're linear here, but we're saturated. And there's a point right about here known as the knee. That's an important thing to know because as the designers build their transformers, they operate in this linear region all the way up to, and some even into, that knee. Let's go back and consider this applied field. You could think of this as the drive signal. Technically, it's the amp turns. However, for our purposes, this is roughly equivalent to the voltage. So we have the drive, and then we have the effect. So you may attempt to establish a magnetic field in that transformer, and then this here shows what that magnetic field is. Well, this is fine in the linear part because there will be a linear relationship between cause and effect. And that will occur right up to the point where we have this knee. However, if you go any further than that, you'll reach core saturation. In practice, this means that once you pass the knee, the transformer is no longer operating like a nice transformer anymore. As you'll see in a moment, once the drive passes the knee, the input current will increase at a very rapid rate. In fact, applying more voltage on a winding than it's rated for is a very quick way to destroy a transformer. Let's do a quick review and then we'll move to the actual testing. Here is the transformer of interest. We're going to apply a variable voltage to this input. We are going to measure the current with this current transformer. Not shown is a variac, which we'll use to adjust the input voltage. And of course, we'll connect up an oscilloscope. We've passed 10 turns of wire through the aperture of this transformer. And we've installed a 100 ohm burden resistor. The result is not a 10 amp will read 1 volt, but 1 amp will read 1 volt. Remember, we passed the wire through the aperture 10 times. Therefore, it's not 10, but 1 amp will read 1 volt. And now we move to the oscilloscope to see those voltage and current waveforms. At this moment in time, I have channel 1 set to 20 volts per division, and I've got the cursors on, so you can see that the peak of that waveform is about 34 volts. Why 34? Well, it's a 24 volt transformer. 24 times root 2 is about 34. So we've taken that 24 volt RMS and we've converted it into a peak voltage. We've set the variac to provide that peak voltage into the 24 volt winding of the transformer. Now we can turn on the current, which is displayed on channel 2. You'll notice that the current is not symmetrical. It has peaks occurring at the voltage zero crossing. Another way of saying that is there's a 90-degree phase shift between the voltage and the current. Keep in mind that there is no load on this transformer at this particular time. As for the calculations, we see that this current waveform has a peak of about 1.4 divisions. And since the oscilloscope is currently set to 0.2 volts per division, that means we have 0.28 amps of current in the transformer. You'll recall our previous conversation where we had 10 wraps through the aperture of that transformer. Because of that, there's a one-to-one relationship between the voltage as measured on the oscilloscope and the actual current in the device. Now, watch what happens when we increase the voltage. We're now at an input of about 40 volts peak, and I would argue that there was a mostly linear relationship, right? The voltage went up and the current went up roughly the corresponding amount, but watch this. You can see that a very small change in voltage has now resulted in a very large change in current, and that's happening because that core is saturating. Right? So if we're down here, we could argue that it's a linear relationship. As voltage changes, current changes. However, once you pass a certain point, a small change in voltage will result in a large change in current. Let's go ahead and move channel 2 so we can view more current. So here we are with 40 volts peak going into a transformer designed for 34 volts peak. Watch what happens when we go to 60. You can see that current just rockets up. We now have over 4 amps peak going into that transformer winding. Let's set channel 2 to 5 volts per division. Here we are with 20 volts into the transformer, 40 volts peak, 60 volts peak. We'll try for 80. I wouldn't want to stay here very long because we'll cook the transformer. And you can see that we had over 15 amps into that winding. At any rate, I think the point's been made that transformer core will saturate when an excessive voltage is applied to any individual winding. It's safe to say that transformer simply would not survive under those conditions. As for next steps, make absolutely certain that you understand the dangers associated with a current transformer and why a current transformer must always have a burden resistor attached to it. Also, you may want to do some experiments dealing with core saturation as a function of frequency. Best wishes to you in your experiments. Please leave any comments, questions, or concerns in the space below.